Have you ever wondered if you should try running your R scripts as a serverless function? Have you followed tutorials and wondered if there is a better way? I did, and I'm going to share with you what I've learned along the way and how I made serverless data science a little bit better than I found it. I'm Peter Solomos, biologist, data scientist, and co-founder of Analytium. I build data analytics pipelines and web applications using R. I value resilience, freedom, and simplicity, and I expect data engineering solutions to align with these values. Let's see what I mean by that. But first of all, why bother? What is the most common reasoning for a serverless architecture? This is what I call a coupled analytics architecture, where the front end is server-side rendered and is in constant communication with the backend. This is the design behind Shiny and is best suited for exploratory applications that involve a lot of reactivity at the level of the data. You can see here that cost is proportional to the resources required by the front and back end combined. This can easily lead to a constant margin. Other applications do not require the same kind of reactivity and statefulness. As a result, we can get away with fewer round trips between client front end and backend. Imagine a Plumber API as the backend and static HTML or any JavaScript framework as the front end. We can push most of the reactivity to the client side. Decoupling of the backend analytics from the front end also means now we are not bound to Bootstrap and can optimize the bundle utilizing tree shaking, code splitting, and lazy loading. After these convincing arguments, let's see what do I mean by resiliency. Here's a backend API, a microservice. It has two endpoints. The first depends on packages 1 and 2, and the second function depends on packages 2 and 3. You might use Plumber for this API. As you make changes to the first endpoint, you update package 2. This breaks endpoint number 2. Of course, if you use unit tests, this will never make it into production. But even in that case, you have to fix bar before you can send it to production. That's extra work fixing something that worked perfectly fine before. What if we used containers to isolate the two functions? Updating foo has no impact on bar. This is where Docker and similar container technologies come into the picture. Docker provides immutability for the image layers. This makes it easy to version images, test and release, or even roll back changes. You can even deploy both versions to roll out gradually or to experiment. Isolation prevents conflicts that you saw a moment ago. It also simplifies managing resources at the container level, such as memory or CPU limits. You can read more about the state of container technology in R from this paper by Daniel Nust et al. Next is freedom, free as in free speech. Here are the 3 largest cloud providers and a very brief summary of their function as a service offerings. Note also that each of these vendors has its own CLI. That means there's an R package wrapping that CLI. This leads to repeated efforts and makes migration less straightforward. I see both of these as potential risks. As an owner, I have less control over costs. As a consultant, I'm niching down into a segment defined by a vendor. What is common in all 3 is that there is no R runtime. Therefore, you have to use containers. Managing containers at scale is not trivial, and managing serverless infrastructure is also often outsourced to public cloud providers. This is where OpenFaaS comes in. The OpenFaaS project was born to mitigate these problems and to avoid vendor lock-in. OpenFaaS is an open source framework to deploy functions and microservices anywhere at any scale. The project was created by Alex Ellis and is maintained by the OpenFaaS core team and the community. OpenFaaS has an emphasis on Kubernetes. It provides auto-scaling metrics an API gateway, and it is language agnostic. So what's Kubernetes? Kubernetes is a container orchestration engine for automating deployment, scaling, and management of containerized applications. As you can see in this graph, the cluster consists of a set of worker machines or nodes that run containerized applications. The worker nodes host the pods that are the components of the application workload. The control plane manages the worker nodes and the pods in the cluster. OpenFaaS is great at abstracting away unimportant details and creating a simple multi-cloud experience where the user is still in full control. Let's outline what function we are going to build. The function takes some request parameters. Based on that, retrieves data from an API that contains daily COVID-19 case counts based on the Johns Hopkins University's global dataset. Then we fit an exponential smoothing time series model to these observations. Finally, we make a forecast and send a response containing these expected values and prediction intervals around them. This is what the observed case counts look like for Canada, and the white lines and blue ribbons indicate forecasts done with two different subsets of the data. So we want the function to return the numbers that we can use to draw the white line and the blue ribbons. Step 0, set up your cluster. This can be a local cluster using Kindi, Kubernetes in Docker, Minikube, or K3s. It can be a managed Kubernetes offering by one of the many cloud providers, or it can be a server with the lightweight faas-d, which is a stripped-down single-node cluster. Check out the OpenFaaS docs for instructions and tutorials. Next step is to install the faas-cli. It is available for different operating systems, including Windows PowerShell 2. This is the step where the instructions deviate from all other templates. Instead of a Go, Node, or Python template, we are going to pull templates for R. Templates are in the nlithium/openfaas rstats templates GitHub repository. We can use the faas-cli template pull command to do this. There are 18 templates based on the parent Docker image and the framework being used. You can choose between 3 parent images. The Debian-based Rocker R-base represents the bleeding edge. The Ubuntu-based R Ubuntu is for long-term support, and it uses RSPM binaries for faster R package installs. The Alpine-based R Hub R Minimal has the smallest image size. Think of 36 megs. stdio passes in the HTTP request via standard input and reads the response via standard output. Other HTTP frameworks like HTTP UV, Plumber, Fiery, Beaker, and Ambiorix are all packages that you can find in the R ecosystem. Each of these frameworks has its own pros and cons for building standalone applications. Let's pick Plumber with the R base image. Plumber is one of the oldest of these frameworks. It has gained popularity, corporate adoption, and there are many examples and tutorials out there to get you started. Now that we made the decision of which template to use, the next step is to create a new function. The template naming follows rstats, parent image, server framework pattern. We define 2 environment variables, one for the Docker Hub username or any other registry prefix. The second is the IP address or domain name for your OpenFaaS cluster. We pass the template name, the function name, and the prefix as CLI arguments. I'm sure you started wondering if I'm going to ever show R code at this R conference. Here you go. This is the handler.r file inside the newly created COVID forecast folder, which is going to be the name of the cloud function. According to the familiar Plumber annotation, following #*, we define an endpoint at the root. Plumber will pass URL parameters to the function as arguments. Inside the function, we do some type conversion and call the COVID forecast function that spits out the forecast information that will be formatted as JSON as part of the response body. You can see what parameters can be passed to the function. If your handler requires extra packages, you can add those to the description file. Here we import forecast. For other use cases, you might need to add remotes, system requirements that will be installed into the Docker image before attempting to install R packages. You can also pin R package versions. Finally, we are ready to build the Docker image, push it to the Docker registry defined by our prefix, and deploy the function into the OpenFaaS cluster. You can do all this with one op command, or you can do it in 3 steps, especially if you want to test the Docker image locally before pushing and deploying. When all this is done, it is time to invoke the function. Go to your OpenFaaS URL /function/function name, provide some parameters, and this is the JSON you can use on the front end to provide a numeric summary or draw an interactive graph. If you got excited about replicating this example, head over to openfaas.com/blog/rtemplates, where I have recently written up this as an example. To recap, use the faas-cli to create a new function, edit the handler.r file, put here also data you might want to load for a scoring engine and so on. Define the dependencies. Build, test, push, and deploy. Once the cluster is ready, you can invoke the function. We all know how well R is suited for data science due to its diverse tooling and its ability to leverage and integrate with other languages and solutions. I believe that R can truly shine in the multilingual serverless landscape. Thank you for listening to me talking about serverless data science in R using OpenFaaS. You can find and read about the R templates for OpenFaaS in these GitHub repos and find examples at nlithium OpenFaaS rstats templates and rstats examples. Feedback and contributions are much appreciated. Cheers, and let's open the floor for questions.